Hello students, welcome to the video lecture of our fourth colligative property, osmotic pressure. See students, till now we have covered three colligative properties, that is relative lowering of vapor pressure, elevation of boiling point and depression of freezing point. Today we will take up the fourth colligative property, that is osmotic pressure. Okay, but before going through this video lecture, if you have not watched the earlier videos, I would suggest you to watch those videos first and then come to this topic. Okay, so students, see, our today's topic is osmotic pressure. See, to understand osmotic pressure, we need to first understand what is osmosis, right? And to understand osmosis, we need to first understand what is semi-permeable membrane. Okay, so we will start our topic with the semi-permeable membrane. See students, as the name suggests, semi-permeable membrane. In short, we write SPM. Right? Now see, as the name suggests, semi means half or partial. Permeable, permeability is the permission to allow, to go, right? So it is nothing but allowance or to allow. Permeability means to allow and membrane means a membrane, right? So students, a semi-permeable membrane is basically a membrane which will allow the solvent molecules to pass through it while restricting the movements of solute molecules, right? So suppose you have a membrane like this. See, suppose you have a membrane like this. So what will happen? Here I take solution. My dear students, as you know, solution consists of your solute and solvent. So this particular membrane, it will not allow the solute to pass through it, but it will allow the solvent molecules to pass through it. Such a membrane is known as semi-permeable membrane. देखने में तो वो आपको एक continuous membrane की sheet की तरह ही लगेगा, but it will have very tiny pores through which only the solvent molecules will be able to pass. So students, we define semi-permeable membrane as the membrane which allows the solvent molecules to pass through it while restricting the passage of solute molecules is called a semi-permeable membrane, right? Now students, semi-permeable membrane can be of two types. They can be natural semi-permeable membrane or it can be artificial or man-made semi-permeable membrane. Natural semi-permeable membrane, students, they generally occur as membranes below the skin of plants and animals, right? A very well-known example of a natural semi-permeable membrane is bladder of pig, right? The urinary bladder of pig acts as a semi-permeable membrane, whereas the examples of artificial semi-permeable membranes include your cellophane paper, students, parchment paper, right? These are artificial semi-permeable membranes. Now I have a precipitated substance having formula Cu2 Fe CN6, right? This substance is a precipitated substance and it is the best known semi-permeable membrane available to us. Okay, my dear students, this is a complex compound or a coordination compound which you will study this year later on. Okay, So right now we will not worry about the IUPAC name of this compound, but I can name it as copper ferrocyanide. This is the name of the substance, Cu2FeCN6. Why I have put square bracket? Students, see, this is the complex part of this substance, and copper is the counter ions which we have put to balance the valency. Don't worry about all these things right now. This you will study later on in your 12th standard. Okay. So this is all about semi-permeable membrane. Okay, students. So our next topic is osmosis. So let me draw a figure first to explain you what osmosis means. See students, here I have taken two containers. This is my container number 1 and this is my container number 2. Right? In container 1, I have filled pure solvent. In container 2, I have taken solution. That is, I have mixed some solute in the solvent and made a solution. Now, in between them, I have placed a semi-permeable membrane. Right? I will write semi-permeable membrane by SPM. So, what will happen? Think. The solute, because here there is no solute and here there is solute, so solute will try to move here. But as we know that this movement is not possible, because semi-permeable membrane allows only solvent molecules to pass and not the solute. So this particular movement is not possible. So what will happen? The solvent molecules will try to pass through semi-permeable membrane. Now students, this can happen in two ways. The solvent molecules will pass like this, or the solvent molecules may pass like this. Correct? Now which of the two will happen? Actually both will happen. Solvent molecules will pass from container 1 to container 2, or solvent molecules may also pass from container 2 to container 1. But the passage of solvent molecules from 1 to 2 will be much higher as compared to the opposite movement of solvent. Right? Why is it so? Because here the amount of solvent is more. So of course from container 1 the solvent molecules will pass to container 2. Okay. So here this movement, the movement of solvent molecules from 1 to 2 will be more as compared to the movement of solvent molecules from 2 to 1. And this process is known as osmosis. This process is called osmosis. So students, how can we define osmosis? Osmosis is defined as the flow of solvent from solvent to solution through semi-permeable membrane. Is that very easy, students? What is osmosis? Osmosis is nothing but the flow of solvent from solvent to solution through semi-permeable membrane. Students, I find this definition incomplete, because here the solvent is moving from solvent to solution and also from solution to solvent, right? So I should write the net movement or the net flow, right? Net flow kyun? Because the movement of solvent from 1 to 2 is more than 2 to 1. So I should use the word net here. So the net flow. One more word should be mentioned here, and that is spontaneous. Spontaneous. Why, students, I am using the word spontaneous? Because this net movement of solvent which is occurring from 1 to 2 is occurring on its own, right? We are not providing it the help of any third agency for the movement to occur. So as a result, it is net spontaneous flow of solvent from solvent to solution through semi-permeable membrane. Very simple. Now students, the same scenario, you consider it like this. Suppose here in place of solvent I take solution 1 and here I take solution 2, right? Now students, assume that solution 1 is dilute and solution 2 is concentrated. Solution 1 is dilute and solution 2 is concentrated. So as a result, what will happen? The solvent molecules will flow from dilute solution to the concentrated solution through semi-permeable membrane. Now my dear students, this is also an example of osmosis. Okay, so osmosis can occur between solvent and solution having semi-permeable membrane between them, or it can occur between a dilute solution and a concentrated solution having semi-permeable membrane between them. So I need to mention here that the net spontaneous flow of solvent from solvent to solution or from dilute to concentrated solution through semi-permeable membrane is called osmosis. Correct? Now my dear students, this is the complete definition of osmosis now. Okay, you have to understand the importance of each and every word that I have mentioned here. Okay, so to revise it, it is the net. Why? Because movement of solvent occurs in both the directions. The net spontaneous flow of solvent from solvent to solution or from dilute solution to concentrated solution through semi-permeable membrane is called osmosis. Right? अब एग्जाम में बच्चों मान लो आपको ऐसा क्वेश्चन आ जाए कि दिस अरेंजमेंट इज गिवन टू यू, ठीक है, एंड यू आर गिवन के दिस इज योर सॉल्वेंट एंड दिस इज योर सॉल्यूशन and there is a semi-permeable membrane between them. So in which direction the solvent will flow? Right? So solvent will flow in both the directions. Right? Now if they ask you what is the net movement of flow of solvent, so net movement of flow of solvent is from solvent compartment to the solution compartment. Correct? It is very easy to understand. Right? So this is the definition of osmosis. Now students, let us understand what do we mean by osmotic pressure. Now, to make you understand this, just think like this, that this solution is at a pressure of P atmosphere, right? And this solution is also at the pressure of P atmosphere, right? Before the start of osmosis, both of them are under the pressure of P atmosphere, right? Now because of osmosis, what will happen? The level of solution here will rise, correct? Because of osmosis, the level of solution will rise. As a result, the pressure will also rise, right? So slowly the pressure will rise, and then it will reach to one particular value that the process of osmosis will stop, right? So suppose when it reaches the extra pressure of pi atmosphere, the process of osmosis is stopped, right? And at this point of time, students, we say that now both the solutions or the solvent and the solution are in equilibrium with each other, because at this particular time what will happen, the rate at which solvent will flow from container 1 to container 2 will be same as the rate at which the solvent will flow from container 2 to container 1, and hence we say that equilibrium has been established, and thus the process of osmosis stops, or I should say thus the net process of osmosis stops. So this extra pressure pi is responsible for the process of osmosis to stop, and this pressure is known as osmotic pressure. So let us define osmotic pressure. Osmotic pressure, students, is defined as the minimum extra pressure that is applied on the solution to prevent the process of osmosis is called osmotic pressure. Correct? So, what is osmotic pressure? It is the minimum extra pressure. Right? It is the minimum. See students, here each and every word is important. Why we are using the word minimum? Because if the pressure is less than osmotic pressure, then process of osmosis will occur. If it is equal to osmotic pressure, the process of osmosis stops. And if it is higher than the osmotic pressure, then what will happen? Then I'll teach you after some time, the process of reverse osmosis occurs. So here the minimum word is very important. Extra pressure. Extra pressure word, why it is important? Because this P, which was the initial pressure or which was the pressure before the start of osmosis, is not to be considered in osmotic pressure. This pi, the extra pressure, is to be considered in osmotic pressure. Now students, think like this. We have the same arrangement, right? Here I have P atmosphere pressure, and suppose that here before the start of osmosis I have applied pressure equal to P plus pi. That extra pi atmospheric pressure I have applied right from the beginning. Then students, think for yourself, will the process of osmosis occur? Of course no. Right? Because when osmotic pressure is reached, the process of osmosis is stopped. So if I apply the osmotic pressure right from the beginning, okay, and the two solutions or different concentrations are separated by semi-permeable membrane, even then the process of osmosis will not occur. Right? So it is the minimum extra pressure, each and every word is important. It is the minimum extra pressure that is applied on the solution to prevent the process of osmosis. Right? That is known as osmotic pressure. Very simple, very clear. Now students, think like this. Let us talk about reverse osmosis. What will happen if the pressure here is more than your osmotic pressure? Now students, think like this. What will happen if I apply pressure here more than the osmotic pressure? So let us consider that here I have your seawater, right? You know that seawater cannot be used for drinking purposes because it has lot of salts dissolved in it. And here suppose I have pure water, right? Or drinking water, which can be used for drinking purposes. Now students, what I do here is, suppose here I am applying pressure more than the osmotic pressure. So suppose here I apply pressure pi dash, where pi dash is more than my osmotic pressure pi, right? So when I apply here on this side, if I apply pressure more than osmotic pressure, then students, you will find that the solvent molecules, the net movement of solvent molecules will be from container 2 to container 1, right? The net movement of solvent molecules will be from container 2 to container 1. So as a result, what will happen? Here we will collect pure water. Okay. So students, this is the method which is generally used for desalination of seawater. For desalination of seawater, right? In this method, what they do, they take seawater and in that particular compartment they apply pressure which is higher than the osmotic pressure. So what will happen? Your solvent molecules, that is water molecules from the seawater, will start moving through semi-permeable membrane to the other compartment in which there is pure water, and thus we obtain pure water from seawater. Okay, so this method is known as desalination. Desalination, it means removal of salts from seawater. Okay, but two things, a very good quality of semi-permeable membrane is used here, and my dear students, the semi-permeable membrane which is used in this process is cellulose acetate. It is an artificial semi-permeable membrane and of very good quality. Okay, and the second requirement is very high pressure. Very high pressure is applied here, right, to obtain pure water in the first compartment. Okay, so this is about reverse osmosis. Okay, students, let us now understand the mathematical form or derive mathematical equation for osmotic pressure. Right? Now, as we know, students, that osmotic pressure is a colligative property. Okay, why it is a colligative property? Because osmotic pressure mainly it depends upon the concentration of the solution. More concentrated the solution is, more will be the movement of solvent molecules to the solution compartment. Okay, so it does not depend upon the nature of solute, but it depends upon the concentration of the solution, and hence osmotic pressure is a colligative property. Okay, now it has been experimentally proved that, students, osmotic pressure pi is directly proportional to the concentration of the solution. वो तो होगा ही, because it is a colligative property, and osmotic pressure pi is also proportional to temperature. Right? So combining these two, I can write pi proportional to Ct. ठीक है? Now, to remove this proportionality sign, we need a constant. So as a constant, I will take here R. R is my gas constant. Correct? So I will take R as my gas constant here. C is concentration of solution. And T is temperature. Of course in kelvins. And pi is osmotic pressure. Correct? Now students, can you see that this equation is similar to the ideal gas equation that you have studied in gaseous state? No? Okay, let's see. Students, this concentration term that we have taken here is in molarity. Correct? Remember, in all the other units we have taken molality, because all the other units involve change of temperature. Correct? And molality is independent of temperature. But here there is no change of temperature. Temperature remains constant during the process of osmosis. So as a result, I can take molarity here. So this is molarity. Now students, as we all know, that concentration in molarity is equal to number of moles of solute, I will write it as N2, upon volume of solution in liters. Correct? So what the equation becomes? Pi is equal to number of moles of solute upon volume of solution into RT. Take V on this side, you get pi V is equal to N2RT. Correct? Now students, this equation, it resembles your ideal gas equation, right? It resembles ideal gas equation. Okay, now one more thing I would like to tell you. This equation is also known as Van 't Hoff equation for dilute solution. Correct? Now see students, this is not in your syllabus, just to make you understand that why this equation is resembling ideal gas equation. So Van 't Hoff, this is the name of a scientist. In dilute, he proposed that in dilute solutions, the solvent molecules will collide with the semi-permeable membrane in the way very similar to the gas molecules colliding with the walls of the container, right? That we have studied in gaseous system. So just as the gas molecules collide with the walls of the container, in the same way the solvent molecules will collide with the semi-permeable membrane, right? And as a result, Van 't Hoff, even he went to the extent of proposing that the solute molecules in your dilute solutions behave as gas molecules. Correct? I repeat the statement again, that solute molecules in a dilute solution will behave as gas molecules, right? And hence this equation resembles the ideal gas equation, PV is equal to nRT. Okay, now this particular equation, students, can also be used to find out the molecular mass of solute. As we have seen with all other colligative properties, that the colligative properties for a dilute solution is used to find out the molecular mass of solute. In the same way, osmotic pressure can also be used to find out molecular mass of solute. So let us understand how we can find out molecular mass of solute from this particular equation. See, as you know that number of moles of solute N2 can be written as weight of solute upon molecular weight of solute, right? Number of moles is equal to weight of solute upon molecular weight of solute. So if I put the value here, I get pi V is equal to weight of solute upon molecular weight of solute into RT. What I need to find? I need to find out M2, the molecular mass of solute. So now I can write pi is equal to W2 RT upon M2 into V. So students, by this equation you can find out the molecular mass of the solute, right? Pi can be measured experimentally. W2 is the weight of solute, R is your gas constant, T is temperature in Kelvin, V is the volume of solution in liters. Student, mind this, V is the volume of solution in liters. Correct? Okay. Now, because in most of the concentration terms we take the volume in ml, but mind you, here the volume should be in liters. Okay. So if you know all these values, you can easily find out the molecular mass of the solute. One more thing, students, which is again a matter of confusion for most of the students, what value of R should be taken here, right? Now that depends. Your pressure, osmotic pressure, can be in atmosphere or it can be in bar. Volume is compulsorily in liters. So students, R can be taken here in two ways. You can take it as 0.0821 liter atmosphere upon Kelvin mole, or you can take it as 0.083 liter bar upon Kelvin mole. Correct? Because this will be in atmosphere or bar. So according to that you select which value of R you need to take, and volume is in liters. Right? Now students, I have told you earlier that these particular two values of R, we have to take it in gaseous state. Okay, this we are studying solutions, but here again, according to the Van 't Hoff's theory, for dilute solution, what happens, the solute molecules will behave as gas molecules. So as a result, R will have any of these values here. Okay. Now students, osmotic pressure measurement method offers certain advantages to determine molecular mass as compared to other colligative properties. Okay, so let us understand advantages of osmotic pressure measurement to determine molecular mass over other colligative properties. Correct? So what advantages osmotic pressure measurement method has in determination of molecular mass over other colligative properties? The first advantage is that it uses molarity instead of molality. Right? See students, in all the other colligative properties we have used molality, but in osmotic pressure measurement we are using the term molarity. So again, that is the advantage. Second is value of osmotic pressure for dilute solutions is large as compared to other colligative properties. Now students, suppose we measure relative lowering of vapor pressure, then its magnitude is very small for dilute solutions. Also, elevation of boiling point and depression of freezing point values are also very small for dilute solutions. Right? It is so small that it makes difficult to measure those values. Okay, but osmotic pressure measurement even for dilute solutions is much larger as compared to other colligative properties. Hence, osmotic pressure can be easily measured, and hence we can determine molecular mass using osmotic pressure conveniently as compared to other colligative properties. The third is, see students, osmotic pressure is a method of choice. It is a method of choice for finding molecular mass of biomolecules and polymers. Now students, biomolecules means the molecules which are present in the living system. Your protein, carbohydrates, fats, right? These all are your biomolecules. Now, as we know, suppose if I take the example of protein, so as you know that protein is highly unstable at higher temperature, right? Or protein gets denatured. What is denaturation? Denaturation is the deformation of the structure of protein at higher temperature. So what will happen here is that because their biomolecules are unstable at high temperature, correct? And hence elevation of boiling point method cannot be used for measurement of molecular mass of such molecules. Okay, and polymers, students, will have poor solubility, right? So this makes other colligative properties difficult for determination of molecular mass of polymers. But osmotic pressure, this problem, you will not find this problem with osmotic pressure, and hence osmotic pressure is the method of choice for determination of molecular mass of biomolecules and polymers. Okay, now students, let us understand the types of solutions based on osmotic pressure. Correct? Now students, based on the type of osmotic pressure, we have three types of solutions. The first is isotonic solutions. Right? Now what does isotonic solution means? Students, isotonic solutions are the solutions, so two solutions having same osmotic pressure at a given temperature, or you can even write at same temperature, are called isotonic solutions. Okay, let us understand it like this. Suppose students, these are two solutions, right? I call this solution 1, I call this solution 2. Suppose these two solutions have same values of osmotic pressures, okay, at a given temperature. So temperature will also be equal, right? T1 is equal to T2. मान लो इसका temperature at T1, इसका temperature at T2, तो T1 equal to T2. Temperatures are also equal. Then these two solutions are known as isotonic solutions, right? And now I would like to mention one thing here, that isotonic solutions have same concentration. Correct? Isotonic solutions have same concentrations. How? So I'll explain it like this. Suppose two solutions, the osmotic pressure of first solution is pi 1 and the osmotic pressure of second solution is pi 2. They are equal osmotic pressures. Now students, just apply the formula of osmotic pressure we have studied just now. So concentration C1 into RT1, correct? This will be formula for pi 1, and C2 RT2 will be formula for pi 2. So we know that T1 equal to T2. So R gets cancelled, T1 T2 gets cancelled because T1 equal to T2. So what we get, C1 equal to C2. Hence this proves my statement that isotonic solutions have same concentrations. Correct? Students, this particular line will be helpful to you in solving your JEE and NEET MCQs. Okay? So keep this thing in mind. Okay? Now, students, the blood cells that we have, right? So suppose if I take a blood cell, it will be filled with certain solution, right? Suppose this is RBC, your red blood corpuscle. So it will be filled with certain solution, right? So the osmotic pressure of this solution inside the blood cell will be equal to osmotic pressure of 0.9% weight by volume aqueous NaCl solution, right? So the solution which is filled in the blood cell will have osmotic pressure exactly equal to the osmotic pressure of 0.9% weight by volume aqueous NaCl solution. Correct? Now this thing, students, it is used in making injections. Okay, this 0.9% weight by volume aqueous NaCl solution is known as saline solution. You might have seen, right? You might have seen they inject saline directly into the blood, because in doing so it will not cause any problem. It will not create any problem because it will have osmotic pressure equal to that of the blood cells. Okay. Now students, the intravenous injections, I mean the injections which is directly given into the vein, right, or even your eye drops, should have same osmotic pressure of that part in which it is given. Okay, so what they do in pharmaceutical industries, they adjust the osmotic pressure by using NaCl, they may use glucose, they may use alcohol such as mannitol, right, to adjust the osmotic pressure. Okay, so that is the thing. Now let us understand this. Now let us move towards the second type of the solution, students, that is hypertonic solution. Hypertonic solution. So what is a hypertonic solution? A hypertonic solution means whenever you compare the osmotic pressure of two solutions, the solution having more osmotic pressure. Okay, while comparing the osmotic pressures of two solutions, the solution having higher osmotic pressure is known as hypertonic solution. Correct? So for example, the solution of aqueous NaCl which has concentration more than 0.9% weight by volume will be hypertonic solution with respect to your blood. Okay, then the third type of the solution is hypotonic solution. So hypotonic solution is, again, when you compare two solutions, the solution having lower osmotic pressure is known as hypotonic solution. So the osmotic pressure of aqueous NaCl solution having concentration less than 0.9% weight by volume will be hypotonic as compared to your blood. Now students, assume that I have three solutions. The first solution is isotonic. Okay. The second solution is hypertonic. And the third solution is hypotonic. Correct? I have three different solutions. Now what I do is, in the first solution, that is isotonic solution, I will place a drop of blood. Right? In hypotonic also I will place a drop of blood, and in hypertonic also I will place a drop of blood. So see, this is my blood cell. Right? In isotonic solution, this is my blood cell in hypertonic solution, and this is the blood cell in hypotonic solution. Right? Now let's see what happens in the first case. In the first case, the osmotic pressure of both the solutions, the external solution and the one which is present inside the cells, is same. Right? So no net osmosis occurs. So cells will be preserved in that particular solution and they will retain its normal size. Okay, so here no osmosis occurs or no change occurs, no net osmosis occurs. Right? Now in the second solution, students, this outside solution is much more concentrated than the solution which is inside the blood cell. Right? So what will happen? According to osmosis, the solution which is inside the blood cell is dilute and the outside solution is concentrated. Correct? Now you know what happens in osmosis. The solvent will move from dilute solution to a concentrated solution through semi-permeable membrane. So here what will happen? The solution which is inside the blood cell will come out, and as a result the blood cell will shrink. Right? From this it will become like this. Right? So students, what will happen? The cells shrink. Correct? Now imagine the third case. In third case, what happens? The outside solution, the external solution is hypotonic, means it is dilute, and here the solution which is inside the blood cell is concentrated as compared to the external solution. So what will happen according to the process of osmosis? The solvent will move inside the blood cells, right? And as a result, what will happen? The blood cell will swell. It will swell, right? Because it will hold the solution solvent and it will swell. If there is large concentration difference between the both, right? Means if this is very dilute, the external solution is very dilute as compared to the solution inside the blood cell, then what will happen? In that case, once the water holding capacity, okay, or the turgidity of the cell is reached, what will happen? The cell will burst, right? First it will swell, but as more and more solvent enters into the cell will finally burst. So now students, just imagine how dangerous a situation will arise if your injections or eye drops are not checked for their osmotic pressures, right? Suppose if this is the case, then your blood cells will shrink while coming in contact with your injection or eye drop. And if this is the case, suppose if you put a hypotonic solution in your eyes, what will happen? Your eyes will start swelling, okay, and at last they may burst also, okay. So very dangerous situation arises, and hence the osmotic pressure concept, students, it is very important in pharmaceutical industries, okay. Now students, let us understand some phenomena based on osmosis, correct? So now the first example that I'll give you here is your pickles, making of pickles. You all might have seen your mother or grandmother making pickles at homes, right? So what they do is they will take the raw mango, suppose this is a piece of raw mango, right? And they place this raw mango, what they do? They apply salt on it, right? They apply salt on it. As a result, what will happen? You might have seen that this mango loses water, right? Mango loses water and finally it shrivels into a pickle. So what actually is happening here? See, the salt that we are applying, right? That salt solution that you are applying, what will happen? It is much more concentrated than the solution which is present inside the mango. Okay, so what will happen? The water inside the mango will come out by the process of osmosis and finally we get pickle. Okay, the second example is, suppose you have limp carrots. You have limp carrots. So suppose you have a carrot somewhat like this. Somewhat this type of the carrot is limp carrot. Okay, teddy-medi carrots. Please bear with my drawing. Okay, so this is limp carrot. Now if you want to obtain a normal looking carrot from this, what is done? This carrot is placed in water. This carrot is placed in water. So what will happen? It will start absorbing water. It will start absorbing water by the process of osmosis and finally it will convert into your normal looking carrot. Okay, students, the third example is, I can give you, is wilted flowers, murjhaye hue phool, right? They can be made fresh by putting them in water. You might have seen कि आप कभी भी किसी फ्लावर शॉप पे अगर गए हो तो आपने देखा होगा कि जो फ्लोरिस्ट होता है वो बार बार जो उसके फ्लावर्स है, he sprinkles water on those flowers. Now what is the reason? See, wilted flowers, right? Suppose this is a petal of the flower I am showing you. This wilted flower, when it is kept in contact with water, right? This flower, when it is kept in contact with water, what will do? It will start absorbing water by the process of osmosis and it will turn into a fresh flower. Okay. Then the fourth example is, students, meat. To preserve meat, they apply salt on it, and to preserve fruits, they apply sugar on it, right? So meat can be preserved by a process known as salting, and sugar and your fruits can be preserved by applying sugars on it. Okay, now what is the phenomena exactly taking place here? So suppose this is a piece of meat, and what I am doing is I am applying salt on it to preserve it. Right? I have applied salt on it. Okay, now suppose if a bacteria comes, this is the bacteria. Right, this is a bacteria. So what happens is when a bacteria comes and sits here, okay, so this solution is much more concentrated as compared to the solution which is present in the bacterial cell. As a result, what will happen? The bacterial cell will lose water. The bacterial cell will lose water and finally die. Okay, the same is true for preserving the fruits by applying sugar on them. Okay, and this is also the reason that why your mom or grandmother, whoever prepares the pickles in your house, they add a lot of oil, salt and sugar into the pickles so that it can be preserved for a longer time. Okay, one more example, students, you know, you are always advised to not to take large amount of salt in your diet. Okay, so what happens is the people who take lot of salt or they have increased salt intake in their diet, okay, their body will have the tendency to retain more water. Their body tissues will retain more water and that will cause puffiness. Right? ऐसे सूजा हुआ मुंह, बड़ी बड़ी आंखें, okay, and such things will be seen. This condition, dear students, is known as edema. Edema. अगर मैं हिंदी में बोलूं तो सूजन, नॉर्मल लैंग्वेज में सूजन. ठीक है, तो अगर आप सॉल्ट ज्यादा लोगे तो आपके टिश्यूज, जैसे ये सॉल्ट आपके टिश्यूज के कांटेक्ट में आएगा, व्हाट टिश्यूज विल डू, दे विल स्टार्ट होल्डिंग वाटर, राइट, मोर, and as a result what will happen, it will lead to accumulation of water and salt in the different parts of the body and that leads to puffiness, and this condition is known as edema. So many other examples of phenomena that can be explained by osmosis can be given. See students, when you come out of the swimming pool, you find kind of wrinkles on your fingertips, right? Now that also can be explained by osmosis. Opening and closing of stomata can be explained by osmosis. Okay, so osmosis, many natural phenomena occur by osmosis. Okay, hope you have understood today's video lecture. Okay, now students, the next time the video lecture that we'll have will be of Van 't Hoff factor, which is very important. ओके अभी तक तो ये सब टॉपिक्स तो आपने एकदम हल्के में लिए होंगे, आपको यू नो दे आर वेरी इजी और आपको समझ में भी आ गए होंगे. बट नाउ द नेक्स्ट लेक्चर दैट वी आर हैविंग, द लास्ट लेक्चर ऑफ द चैप्टर प्रोबेबली विल बी ऑफ Van 't Hoff factor. Okay, so before moving to that Van 't Hoff factor lecture, students, make sure that you have seen all the video lectures up till here and then you move to the next lecture. I am waiting for your comments. Write in the comment section how did you like this video lecture. Okay, and if you like the video तो like करो and also share the video. Okay, and if you have not subscribed to my channel yet, students, do subscribe to the channel and also hit the bell icon so that you will be notified whenever new video is posted. Okay, so keep studying, keep practicing. Okay, bye for now.